Yeah, so what we'll do is we'll finish this lecture with defining an ADT hash table. And as mentioned, we have two different types of, the major problem with hashing is collision. And to address collision resolution, we do in two different ways. One is called separate chaining and open hashing. Okay. We will define a hash table for separate chaining and close this class. When we talk about separate chaining, let's see how separate chaining is done. We have actually an array of lists. Okay. Let's see how we will define this array of lists. This is for primarily collision resolution. Let's say having indices 0, 1, etc. goes up to 9. And this is a nice hash function which has been defined in Mark-Allen-Weiss. Let's say with the 0th element, some information that is there, and one is, let's say, 81 and 1, and 9 is some 49. Or 9 is some particular hash function like this. So what does this mean here? It means when you did a hash of the key value, it gave you this index, and both 81 and 1 hash to 1. Then what do? We create a linked list. So what we do when you have to search for an element, you give the key value, it hashes to this, then you search down this linked list. Okay. And all these things here. Okay. So it creates for you this linked list, and then you search for the element. So basically, if you want to search for a particular element, we call it the number of probes, and that's what, so essentially hashing, you gets you to this particular index. Then how many ever times you, this is called linear probing, go through this, for example, and find the particular element. This is called the number of probes, which is what is the analysis that we did. Okay. We'll see this analysis in a little bit. Okay. So now, what is open hashing on the other hand? I'm just going to give you an idea about it. I'm not going to, I already mentioned it. You can have two ways of doing it. You can do what's called an overflow area where these linked lists are placed, or you could alternatively hash it to a particular value here. And if it is full, let's say, like that example that we had, just repeating it here, then what you do is I have some new word that comes. Suppose I'm using the first letter of the alphabet. You find the first entry, first table entry which does not have a value, and put that value there. So what happens when you hash, for example, hash of k, it gives you an index into the table. Then you check whether it's there in the particular bucket. If it's not there in the bucket, you sequentially search through this entire table till you find the element. So right now I'm just going to talk about separate chaining and the ADT hash table for this. What will it be? It clearly be an array of this. Okay, what is list now? List is your list ADT. Okay, what are the operations that you want to have? Create a hash table of some particular size. So to create an array of appropriate size, insert key into the hash table. This is of some what you want to do is you want to insert one minute. You want to insert a key and the record corresponding to the key into the hash table. And I'm changing things a bit from what is given in the book because he's using a template and I don't want to as yet use a template class, which we'll do in the lab. Then I want to remove entry from the hash table. Then I may want to find a key in the hash table. And what can each one of these be? So this is our hash table definition here. And a key can be anything. It could be a normal integer. Key can be a string, as we saw. Various type of, depending upon the type of hash function that we have. You can have, if it's an integer, for example, simply key mod percent table size can be the hashed value. Return that. And let us say we have a hash function, which is I want to talk about the hash function that is there in Markov ways. Let's see, it's called hash. What does it do? It returns an index into the array. Hash of, let's say, it takes a string as input and table size also as input, type integer. So basically it has to return what is an index into the table. So let's say we have a hash value, which is of type integer. And what we do is, the idea of this function is like this. Do 0 less than or equal to I less than key string length of key or integer. Let me call it string length of key. That means I'm taking all the characters here, and this particular function just does this. Hash value, let's say it's initialized to 0. Assign the value 0 equals 37 star hash value plus key of I. This is what it does. It's actually a polynomial in some kind of polynomial in 37 end loop. And then finally, of course, because you're given we need the table size. Table size is passed, right? Yeah. Hash value is assigned the value of hash value mod table size. So that you'll get a number between 0 and table size. If just in case your hash value can happen, because if your most significant bit in the character, you'll be learning about this in the computer organization course. As 1, it will think it's a negative number. Hash value is assigned the value of table size plus hash value. So it remains within the table. Okay. Then we end if return hash value. All right. So this is a hash function that we have. Can have many different kinds of hash functions. As I said, for any additional references on various types of hash functions, you could come. We'll do the analysis of this hash table later in your algorithms course. You will learn something about amortized analysis. Yeah, amortized analysis, which will ensure that amortized cost, as it's called, you'll learn more about that, is ordered on for the number of probes. That is, I start, let's say, I have this, in this particular case, for example, I start, let's say, I'm looking for GAN here, and suppose these are filled. So this is the first probe. I came into open addressing here. Then I search through this, go to the next closest location. So if there are n items that are possible in the table, then when will I get to G? What is the average number of, let's say I go and check here, there's something already here, then I move on to the next location. Then I keep searching till I find the particular element. How many probes will be required? You can show when you do a particular analysis called amortized analysis and a particular organization of the hash table that this cost can be reduced to order 1. Amortized analysis is quite different from what we do in worst case time complexity. Okay, so let's see what are the things that we will do now. When you create hash table of, so this is like your make null of size, table size, then let us say we had the array of lists, right? So we'll allocate, you'll make lists equal to some list of some whatever table size. Let's say there's a function like this which can be created. And for do 0 less than or equal to I less than table size, I will make list of I dot make if I'm using the list that we had defined earlier. It will be a make null operation. Then if you want to remove, I want to remove an element. Let's say I have table remove of some key, then I'll get the list of hash of key comma table size, let us say. That's all that I need here. Table size and so dot delete of some X or wherever it may be, key. Okay. Might have some function like this, just to find a particular element and delete. And I'm just assuming there's something that will take the key and find the key in the list and delete it. Then you can have a find of key, which will hopefully return the record or element type of that particular element. Otherwise, it will, let's say this is like list of hash of, I'm not going to complete this because there's some things that we need to know and how to program these things. List of table here again, table size, and dot locate of key, and various things. Okay. And if it's not found, we should send some null. Return null if not found. Not found. Okay. So this is the hash table that we have. Various operations on the hash table that we can define. Right. So let us stop here. And this kind of completes hash tables. I will talk about extendable hashing. This is done when when things are very large to store in memory. See, what happens is when we talked about lists, stacks, queues, and hash tables now, we assume that all these things can be stored in memory. Okay. But as we go along, it's possible that nothing can be stored in memory. You need special data structures where you want to special data structures, or rather ADTs, to access elements on the disk. And we'll talk about this. So extendable hashing is one such, something that doesn't fit into memory. We'll talk about this after doing trees, because there's something called B tree, which is like an extendable hash function used in databases quite extensively. Okay, so we